Hello everyone, here we are going to see about the impulse response and step response for a LTI system. So first we are trying to find the impulse response while representing LTI system, and we are listing out some of the properties. So first of all, we are discussing the first property is commutative property, and this commutative property with respect to the convolution operation, either it is in terms of discrete in nature, can say like this: x of n is convoluted with h of n, which is equal to h of n convoluted with x of n. So if it is in the continuous time nature, it is x of t convoluted with h of t, which is equal to h of t convoluted with x of t. So this will give the condition for commutative property, and we are trying to prove this condition. So the proof for this, we are going to say the consider, we are taking the one particular condition. I cannot prove first together, so I'll just take first as a discrete time LTI system. And if discrete time LTI system, if I consider the impulse response over here, what we considered is h of n, along with the other one is input, that is x of n. So what I need to consider with respect to the first equation, that is x of n convoluted with h of n, I'll take it as one of the condition as the final output I will take over here. The output y of n is nothing but if I convoluted between the two terms, one is input x of n convoluted with respect to something impulse response h of n. So I'll get some output y of n. I'll call it as y of n. So I'll taken that particular condition, nothing but left hand side of the first equation, what you are seeing in this particular presentation, particular slide. So x of n convoluted with h of n, we already know. With respect to the convolution sum, we know the equation for this, that is summation k equal to minus infinity to infinity x of k into h of n minus k, where x of k is a part of input, h of is impulse response unit. So we know this from the convolution sum, and we expanded this further as by substituting for n minus k. So we have h of n minus k, where we are going to substitute the value for n minus k, which is equal to something like m. So h of n minus k changed into h of n, as you can see, but x of k, whatever I considered, the k, if I take it with respect to n and m, so it becomes n minus m. So that's why the equation now further it will be changed. Y of n is equal to m equal to infinity to minus infinity x of n minus m into h of n minus m. So what you are observing, the factor of summation factor is changed in terms of k to m here, but the along with the time value is minus infinity changed into infinity in the lower unit, in the upper unit infinity changed into minus infinity. This is what the changes which we changed. But so I can rewrite this as m equal to minus infinity to infinity for the summation, that is same, because the time unit, whatever the value existed from minus infinity to infinity or infinity to minus infinity, if you consider, so this will give always the positive values. It will not depending upon these values, it will give something positive. Though either you can change the summation, the lower order or upper order. So how, by that condition, I can rewrite this equation y of n, which is equal to summation m equal to minus infinity to infinity, so h of m into x of n minus m. So this now, this entire equation now, this particular line, which is going to look in terms of convolution between h and x. So that's what we can write now with respect to y of n, which is equal to h of n convoluted with x of n. I started with y of n as x of n convoluted with h of n, but I ended up here, which is equal to y h of n convoluted with x of n. Hence the commutative property, which is proved for the discrete time nature of the signal in terms of convolution sum. So similarly for continuous time also, we can able to prove that a system has an impulse response in terms of h of t and with input x of t. So I'll consider now with respect to continuous time signal. So let us look over here. So we have, let me consider as similarly for the discrete nature what we considered, same we need to do the conditions like y of t is equal to, I'll take h of x of t is input, h of t is the impulse response what I considered. So with respect to this, we know the convolution integral equation will be integrated from minus infinity to infinity x of tau into h of t minus tau d tau. But the same substitution, however, we did it earlier with respect to the commutative property onto the discrete nature. Substitution require for h of the terms. So over here also h of terms is required the substitution. That's why we'll take t minus 2 equal to some new term as m. So if you take the differentiation for this, this is in terms of tau is defined here, it is defined in terms of m. So minus d tau into dm, then the integration values will be changed now for y of t, that is integration. Now the lower unit changed into infinity and minus infinity as the upper unit, because if tau is defined minus infinity, tau equal to minus infinity, what could be m? M should be in positive infinity. So when tau is equal to infinity, what could be m? It is changed into minus infinity. So the d tau will be changed over here into dm, so that with the negative sign, so that's why this negative sign is indicated. So y of t is now, after substituting for t minus tau is equal to m, so we'll get the minus of integration infinity to minus infinity, x of tau is changed as t minus m, and t minus tau will be defined as m. So that's why the equation for y of t is changed into this. So now I'll rearrange this in terms of the changing the integration limits, upper limit to lower limit to upper limit. Then there should be existence of negative sign. So negative sign will appear over here. So the negative will become positive here. So y of t becomes integration minus infinity to infinity. I'll write h of m first, and then I'll write x of t minus m into dm, and this now looks convolution integral between h and x. So that's why I can write y of t is equal to h of t convoluted with x of t. So this now changed, starting from y of t I considered as x of t convoluted with h of t. So now this equation says convolution integral is also follow the commutative property. So that's why in these both cases what we observed for either convolution sum or convolution integral, though you take, the convolution operation is always commutative. Hence, with the help of impulse response h of t or h of n, I observed this commutative property. So next we will discuss about the distributive property. So if I comes into the distributive property and I can list out the distributive property for in terms of continuous nature and discrete time signals, we are going to be represented in this order. So it says x of n convoluted of h1 of n plus h2 of n. There should be a two set of impulse response which is equal to x of n convoluted with respect to h of n, and x of n is convoluted with respect to h2 of n should be added together. So this is what, with respect to discrete nature, how we can represent distributive property. But for a continuous nature, how it can be represented distributive property, it says with this equation x of t convoluted with respect to h1 of t plus h2 of t, which is equal to x of t convoluted with h1 of t plus x of t convoluted with h2 of t. So the proof for this, I'll start with the first one, that is discrete time signal. I'll consider first. So the discrete time signal, if I consider the first condition, so over here the right hand side we have two sets, that is x of n is convoluted with respect to h1 of n, so I'll take as y1 of n. So x of n convoluted with respect to h2 of n, so I'll take this condition as y2 of n. So I'll have now the, with respect to the right hand side, for the convolution some condition or the discrete nature condition, I'll have y1 of n and y2 of n. So if I add these together, that is what the right hand side of the distributive property for discrete nature. So the final y of n I considered in terms of y1 of n plus y2 of n. That means x of n convoluted with respect to h1 of n plus x of n convoluted with respect to h2 of n. So if I expand this particular condition, so the first set x of n and h1 of n, hence it is summation k equal to minus infinity to infinity x of k into h of n1 h1 of n minus k, and the second term x of n convoluted with respect to h2 of n, so that I can represent it by the convolution sum as summation k equal to minus infinity to infinity x of k into h2 of n minus k. So now I'll club these together here, summation and x of k is common, I'll take outside, so summation k equal to minus infinity to infinity x of k, then within the bracket I can write h1 of n minus k plus h2 of n minus k. So this now I'll say h1 of n and this is h2 of n. So if I remove the convolution condition here, so it is observed that this is the first set x of n and this is the second set as in terms of h set. So it need to be represented h1 of n, it need to be represented h2 of n, hence the final answer y of n is equal to x of n convoluted with respect to h1 of n and h2 of n. So this proves the distributive property for convolution condition, especially with respect to the discrete in nature. Similarly, we can try it for the continuous signal also. But one more property which is also required to understand is associative property. So very similar to the earlier two cases, distributive property or commutative property with respect to the either continuous or discrete nature, we observed it and we proved it. In a similar manner, we have to look for associative property both in continuous and discrete time nature. So if I take the discrete time nature, so how I need to be represented the associative property by using a convolution. So it says x of n convoluted with respect to h1 of n convoluted with respect to h2 of n, so which is equal to x of n convoluted with respect to h1 of n, and it is convoluted with respect to h2 of n. So this is what vice versa condition which is observing, and we have to prove this with respect to the both cases, either continuous or discrete nature. Discrete nature also we can just mentioned as per the equation, but in continuous nature we can represent it like this. It says x of t convoluted with respect to h1 of t convoluted with respect to h2 of t, which is equal to x of t convoluted with respect to h1 of t, which is convoluted with respect to h2 of t. So now I'll solve this for the continuous time nature. So first of all, the continuous time nature, then I just take the right hand side of the equation in terms of continuous in nature. So as you can see, the right hand side, which is highlighted here, the right hand side equation, out of that the x of t convoluted with respect to h1 of t, which is convoluted with respect to h2 of t. So here I'll take z of t is equal to x of t convoluted with respect to h1 of t. So what is remaining with respect to the right hand side? Y of t, which is equal to z of t convoluted with respect to h2 of t. So I'll just apply the continuous or convolution integral between these z of t and h2 of t. So it says integration minus infinity to infinity z of tau into h2 of t minus tau d tau. So we know that what is z of t. So I'll just resubstitute for z of t in terms of z of tau. I have to be written. So z of tau means it is x of tau convoluted with respect to h1 of tau. So if I expand z of tau, now I just represented over here, that is integration minus infinity to infinity x of neta into h1 of tau minus neta d neta. So substituting this z of tau into the above equation, that is y of t. So y of t says integration, two integration are coming because we are separately taken for z of tau, and also the first equation, that is integration minus infinity to infinity, and another one is integration minus infinity to infinity. These two integration, one is with respect to tau and other one is with respect to neta. So x of neta into h1 of tau minus neta d neta, and the first one equation, that is h2 of t minus tau d tau, so that is also existed with respect to equation. So but we are substituting the values for tau minus neta here. So we are substituting the value of m in terms of tau minus neta. So then the equation now just need to be modified here. So y of t, which is equal to integration, one integration I'll take along with respect to x of neta. So integration tau neta with respect to minus infinity to infinity x of neta. So next integration tau of minus infinity to infinity h1 of m, so the first term, and h2 of, instead of tau I just substitute. Tau means it is nothing but n plus m I need to consider. So replacing tau by n minus n plus m. So it says h2 of t minus neta minus m dm, which is considered, and d neta outside. So this, the within the bracket whatever we written here, so this which is looks like the convolution integral between h1 and h2. But in general I cannot write it, but I'll just represent it that in terms of the convolution, the new term h of t minus neta. So t minus neta just need to be considered because it looks like the integration minus infinity to infinity h1 of m into h2 of t minus neta minus m dm, which is nothing but it is a convolution between the first term and the second term. So I can say h1 of t minus neta convoluted with respect to h2 of t minus neta. So this is the term. So together I will call it as one single term as h of t minus neta. So now the equation simplified as integration minus infinity to infinity x1 of x of neta into h of t minus neta d neta. So but we know this is nothing but the convolution between h1 and h2 in terms of t minus neta what we considered, but this now looks like x of neta and h of t minus neta. If I look, it is again convolution integral between x and h. So that's why we can write that y of t is equal to x of t convoluted between h of t, but we already know about h of t, that is convolution between h1 and h2. So that's why h of t I can write h1 of t convoluted with respect to h2 of t. That's why y of t is equal to, now I can write it as x of t convoluted with respect to h1 of t convoluted with respect to h2 of t. So this is what I substituted, but earlier what I taken for y of t, that is x of t convoluted with respect to h1 of t convoluted with h2 of t. So this is z of t I just taken and convoluted with respect to h2 of t. Then I just keep on simplifying by resubstituting for the inner values, and I got it. It's the reverse condition. Hence the associative property is proved in terms of convolution also. This is in terms of the continuous time in nature. So similar manner we can also use it to calculate for a discrete nature. So one more conditions along with the impulse response, the term which is coming is step response. So we are trying to understand the step response along with these conditions. So let us look forward into the step response of an LTI system. So unit step response of an LTI system are going to be considered here. So the first output, if I take it y of n, that is in discrete nature. So discrete LTI system characterized by an impulse response h of n, and also with respect to x of n as input. So how I need to write this, y of n is equal to h of n convoluted with respect to x of n, where x of n is the input and h of n is impulse response. Suppose the input x of n is equal to unit step function. So n is equal to u of n, then the value of y of n changed into s of n, that is what we will say the step response condition. So therefore the equation now y of n becomes s of n only possible when x of n is changed into u of n, that is only the condition. So s of n is equal to h of n convoluted with respect to u of n. So now I just need to be substituted we'll take the equation from the convolution sum into this h of n convoluted with respect to u of n. So as per the convolution sum, we can write this equation summation k equal to minus infinity to infinity h of k into u of n minus k. So we know that with respect to the unit step response or unit step function, we can write it in terms of u of n minus k should also be 1 only with n minus k should greater than or equal to 0. Otherwise, I can say in terms of k should be less than or equal to n as the condition. In that, under that, u of n minus k going to be 1. Else, it is going to be 0. That's why this s of n now changed with its summation limits as minus infinity to it can reach till n. After greater than n, what we are having u of n minus k is 0, so that is we cannot take it. So that's why summation limited k equal to minus infinity to n with h of k into 1 instead of u of n minus k. So this is how I just proved the condition unit step functions with respect to the nature. Therefore, step response of a discrete time LTI system is a running sum of the impulse response. Similarly, we can calculate the continuous time LTI system. For that also, the step response function we can calculate. So normally, the continuous time nature representation, it is y of t is equal to h of, I'll just represent it here, y of t is equal to h of t into convolution with respect to x of t. So this is a convolution integral conditions for continuous time LTI system. So with respect to this, if suppose x of t is equal to u of t, then y of t I need to be represented as step response condition in terms of continuous nature as s of t. So s of t now changed whenever x of t is equal to u of t. So s of t is equal to h of t convoluted with respect to u of t. So if I take the convolution integral over here, it will become integration tau equal to minus infinity to infinity h of tau into u of t minus tau d tau. So now I just have to be substitute for this u of t minus tau need to be 1. So that is only the possible condition. So we have to say we know that u of t minus tau, which is going to be equal to 1, only t minus tau should greater than or equal to 0. Otherwise, t should be, I can say in terms of, tau, in terms of tau I should say. So tau in terms of tau, it is should be less than or equal to t. Greater than or greater than t, so then the value of u of t minus tau is equal to 0. So we are replacing u of t minus tau is equal to 1 for the limit from minus infinity to till t. After t is not possible because u of t minus tau is equal to 0. So s of t now equation, which is equal to integration minus infinity to t with h of t d tau is going to be considered. So with respect to this one problem which is mentioned in this presentation, so evaluate the step response for given h of n is considered here. So I'll directly take, this is a discrete nature, I'll directly take the solution for this with respect to the step response equation just previously we mentioned. So s of n is equal to we are defining summation k equal to minus infinity to n with h of k. So if n value is less than 0 with respect to this, we are going to say directly s of n is equal to 0. It is not at all possible because u of n is 0 here if n is less than 0. So only the value existed for n greater than or equal to 0 only. So minus infinity to till 0 value cannot be considered. Hence with respect to the given step response equation s of n, I should say summation k equal to 0 to n only existed for half what is h of k, that is half to the power instead of n we have k here, so k need to be considered into u of n will be 1 over this range 0 to n range. We have u of n minus k is equal to u of n value should be 1. So we know this is the equation of a summation k equal to 0 to n with alpha to the power n which is considered, alpha to the power k is considered here. So this is look the pretty standard format. So it says 1 minus alpha to the power n plus 1 divided by 1 minus alpha. So by that we can after simplifying we can get this solution. So 2 into 1 minus half to the power n plus 1 as the solution for this particular problem. So this is one more condition or one more problem which is mentioned in this particular presentation. So it says to be evaluate integration minus infinity to infinity t square plus cos pi t with the delta t minus 1 d tau. So I just need to find the answer for this. This is what I just need to be evaluated. So we already know one condition with respect to the impulse function, that is delta t minus 1. So with respect to that, we know this shifting property, and it says the integration minus infinity to infinity with respect to x of t. If suppose I have delta t minus t naught dt, so this can also be, I can take it the integration of x of t or x of t with respect to the delta t value, nothing but delta value which is mentioned at t delta t minus t naught, nothing but the existence of with respect to the step impulse or impulse function. We have defined the time shifting condition t minus t naught. So value existed at t naught itself for a value with respect to x of t. That's why it says x of t only at t equal to t naught. That is what shifting property. So with respect to the given problem, we have delta t minus 1. So t naught here is 1. So for a given problem, and this entire t square plus cos pi t looks like 6 of t. So I'll just consider that t square plus cos pi t, when the t naught value over here it looks like 1. So t naught t equal to t naught, that is equal to 1. So if I substitute t equal to 1 into the equation, so t square, that is 1 square is 1 plus cos pi t, pi into 1. So cos pi is minus 1. So minus 1 plus 1 is going to be 0. So this is how we can find the solution for the condition. So this is the properties of impulse functions also to be taken with respect to the shifting properties. Thank you.